Okay. Your test tomorrow will look a lot like yeah, basically just going to be a problem like this where the stem is going to be some derivative graph with table of values. So if you look at the previous packet, any of the problems that look like that, you can just make sure you review those. So I would say page 22 through 24, what we've been working on, worksheet 4, and then in this packet here, also, I think page 9, the AP FRQ worksheet 1. So it'll be some variation of this. It'll just be front and back, and it'll be these problems involving like mean value theorem or product rule or chain rule, string value theorem, or L'Hopital's rule. So finding tangent line equation. Any questions about what to expect for tomorrow's test? You'll get to use your calculator, but I need to see all your work. So tomorrow morning, I'll send out a reminder this afternoon. Tomorrow morning, 7:30, I will work through worksheet 6. So if you want to, I'll send out a remind with a link tomorrow morning as well if you want to join virtually, or you can join me here as I work through worksheet 6. Everybody okay for tomorrow? So I'd like to move into preparing for next week's quiz, which is a combination of Riemann sums, differential equations, rate in, rate out. I'd like to focus a bit more on rate in, rate out. This is still kind of like a newish FRQ for us. And then we can, over the course of Thursday, Friday, and Monday, we can also go back and finish off the rest of a packet. And then starting Thursday, I'm going to assign homework, but I'll start checking the homework on Thursday, and we're going to eventually finish off this packet through a series of classwork and homework to be able to get it all done by the 9th or 10th. But there is a rate in, rate out problem that we didn't get to that I want to do from the previous packets. So this is in packet 1 that we were working on yesterday. Okay. Topics review part 1. We skipped over one rate in, rate out that I want to do here. So this is on page 5. Right, this is with calculator. Okay, let me read this problem, and I would like for us to kind of visualize what's going on with this problem before we jump into all the calculator steps. So it says the amount of water in a storage tank in gallons is modeled by a continuous function on the time interval from 0 to 7 hours, okay, where t is measured in hours. In this model, rates are given as follows. Okay, so the rate at which water enters the tank is given by this f of t, 100t squared sine root t. So that's given by this curve here. So so basically, imagine like the faucet just continues to increase in terms of letting water in. So the rate becomes higher and higher. More and more water is entering. The rate at which water is entering the tank continues to increase, right? Okay, so that's part of it. Now, at the bottom of the tank, water is also leaving the container. So, but it's in a more constant state. It's 250 gallons per hour for the first 3 hours, and all of a sudden it's going to jump up to 2,000 gallons per hour from 3 to 7. Okay. And the graphs of F and G, which intersect at 1.617 and 5.076, that's nice that they give this to us. We don't have to find those intersections ourselves, even though we could, but they just save us a little bit of time there. And then there is 5,000 gallons in the tank to begin with. Now, I just want us to kind of help us visualize what's happening to the water level in these periods of time. So can you tell me when is the water level rising and when is the water level falling? So for the first, let me just highlight those intersections that they told us here. So this T is 1.617, and then this T value is 5.076. So for the first 1.617 hours, based off this graph here, what's happening to the water level? Is it rising or falling? Okay. Falling. Why is it falling? The rate at which water level is leaving the tank is higher than the rate at which water level is coming in, right? So I'm going to indicate a red or orange here to indicate that, okay, the water level is falling, right? Because the rate at which water is leaving is higher than the rate at which water level is coming in. Okay, what about for the next interval here from hour 2 to hour 3? What's happening here? It's rising because all of a sudden the rate at which water is coming in is higher than the rate at which water is leaving. So in this interval, water level is going to start rising again. But then this rate at which water leaves jumps from 250 to 2,000. So then between hour 3 and 5.076, what's gonna happen again? Water level is going to fall. Yeah. But then the curve is going to overtake the horizontal line, and it's going to start to rise again. Okay, so I just want to have us visualize. Okay, the water is falling, then rising, then falling, then rising. Okay, do we see that? All right, good. Okay, so part A here. How much water enters the tank during the time interval from 0 to 7? So part A starts off easier. Don't really have to worry about too much of this. Just worry about how much water has entered into the tank. So we know we're only going to having to deal with F of T, but I want to find the amount of water that's entered in, but they gave me the rate. So how do I get from rate up to the gallons? Take the what? Yeah, and definite interval. Okay. So definite interval from 0 to 7 of 100 t squared sine root t dt. Now, do I have to worry about how much water is in the tank to begin with?
Nope.
Okay, why not?
Because it's asking how much water got in.
It doesn't really care about how much water is in the tank. It just wants to know how much has entered into the tank. So we don't need to worry about that initial amount. Okay, so this can go in your calculator. You're going to use X for your variable in your calculator, and also you want to make sure you're in radian mode, never in degree mode. Okay, we should get 8264 gallons. Part B, between 0 and 7 hours, find the time interval during which the amount of water in the tank is decreasing. So, we already visualized what's happening, so now it makes it a lot easier. We know the water is going to be decreasing whenever G of T is greater than F of T, right? Whenever G of T is greater than F of T, then we know water level is falling. So we highlighted that from 0 to 1.617, and again, also from 3 to 5.076. Because G of T is greater than F of T. So the amount of water in the tank is decreasing on the interval from 0 to 1.617 hours, and also from and T is between 3 and 5.076 hours, because G of T is greater than F of T. Any questions with part B? All right, part C says between 0 and 7, at what time is the amount of water in the tank the greatest? So this is application of which theorem here? They're trying to get us to use what? EVT, right? Extreme value theorem, trying to find the maximum, absolute max, absolute min. In this case, we're only asking for absolute max. So I'm creating a sign line here just to kind of help us visualize what we've already knew, just in terms of water level rising and falling. We know that at the beginning, the water level is going to fall. It's going to hit some relative minimum. It's going to rise, hit a relative max, fall, minimum, and rise again to 7. So if I want to find absolute max, I just have to worry about endpoints and valid critical points. I don't have to really test 1.617 and 5.076. I mean, I could, but I'm just doing additional work where I know these candidates are never going to be an absolute max. So really, I only have to worry about testing 3, 0, and 7. And this is where we're going to use that formula with rate in, rate out. So anytime we're looking for any amounts, it's always going to be 3 categories, right? How much is there to begin with? How much has been added into the container, and then how much has been removed. So any amount I'm looking for, I'm going to call it A of T. It's going to be my initial plus the amount added minus the amount removed. So we'll do that for 0, 3, and 7. A of 0 is easy because they're telling us that there's 5,000 gallons to begin with. So to do any work there. To find A of 3, how much is in the tank 3 hours in? We know we have to involve 5,000. That's how much there is to begin with. How much has been added from 0 to 3 of f of t dt? How much has been removed? The integral from 0 to 3. And then 250, right? Because that's the rate. 250 gallons per hour. Now, technically, we don't need calculus for this. We can just do 250 times 3 hours, and we can also just set it up and make it into an integral as well. So this can go in my calculator. Both these can go in my calculator. I add this together, I get 5126.59. Any questions with how I set that up, AF3? Now, we also need to find AF7. Now, here is an option for us to do without having to go through a bunch of more complicated formulas, is what if we just pick up where we left off, right? We already know this is how much we have 3 hours in, so we can just pick up where we left off and then just continue to add and subtract from 3 hours on. So I'm going to pick up where I left off at hour 3. That's going to be my quote unquote initial. And then I'm going to add from hour 3 to hour 7, how much water has been added to that point. And the nice thing about doing this way is I can just kind of pick up where I left off because I know there's a different formula for the amount being removed. It's going to jump up to 7 or 2000. So I don't have to start from scratch. I can just kind of, okay, I already know how much there is at 3 hours. So we just continue to accumulate from 3 hours on. So I'm going to subtract the 2000 gallons per hour from the amount of water that's been added. And this is on top of what we've already gathered at hour 3. So we have 3 candidates, and each of the candidates we can just compare. We were looking for absolute max, so obviously the highest is 5126. So absolute maximum at t equals 3 hours. So typically with rate in, rate out problems, it usually ends with like an EVT application. Okay, that's really all I wanted to do from the remaining pages of packet 1. If we can move into packet 2 and just start working through the variety of problems. Okay, so moving into packet 2. Number 1, this is page 1. Riemann sums with particle motion attached. Let me review a couple of items at the top of the page here. We know velocity is the derivative of position, acceleration is the derivative of velocity. We know total distance is the absolute value, integral of the absolute value of v of t. Average velocity, you can use average value theorem. You can also do change in position over the change in time, depending on what you're given. Increasing speed is when velocity and acceleration at the same time. Decreasing speed is when velocity and acceleration have opposite signs. And then increasing velocity, decreasing velocity is simply asking for the slope of velocity, which is effective acceleration. So when acceleration is positive, my velocity is increasing because my slope of my velocity is rising. Decreasing velocity is when acceleration is negative. All right, so let's look at number one. A car travels on a straight track. During the time interval from 0 to 60 seconds, the car's velocity is measured in feet per second and acceleration is feet per second squared. They're both continuous functions. Table above shows selected values of these functions. Use appropriate units to explain the meaning of the integral of from 30 to 60 of the absolute value of v of t in terms of the car's motion. And then approximate using trapezoid approximation with 3 subintervals. So we know this notation is involving total distance, right? So we see that negative and positive velocity indicates that the direction in which this car is going. Negative velocity means it's moving to the left. Positive velocity means moving to the right. But total distance will tell us how much the car has traveled in terms of the odometer reading, and regardless of direction. So if it's regardless of direction, and we want to use trapezoid approximation, what do we need to do with all these negatives here? Yeah, we need to think of them as positive, right? We need to think of that. Okay, so this is, even though it's moving left, total distance, we don't really care about direction, so we just want to know how much progress or how much distance has it gone regardless of direction. So we can just say that, okay, this notation means the total distance that the car travels in that 30 to 60 second range. In part A, your trapezoid, remember your area formula for trapezoid is 1/2 width, height 1 plus height 2. Literally. So from 30 to 60, my interval here, 30 to 35, that's a width of 5, 35 to 50, that's a width of 15, 50 to 60, that's a width of 10. And I'm just kind of going through my trapezoid approximation, creating 3 separate trapezoid area formulas and adding them together using my calculator here. Part B, using the appropriate units, explain the meaning of the depth interval from 0 to 30 of A of t in terms of the car's motion. Find the exact value of the interval from 0 to 30 of A of t dt. So this is rely on first theorem, right? First theorem, we can evaluate the step integral here. We know acceleration is going to rise up to v of t, and to f of v minus f of a, right? So v of 30 minus v of 0. So if we go through first theorem, v of 30 minus v of 0 is a lot easier to think about what that means, right? We're taking the velocity at 30, we're taking the velocity at 0, and we're just subtracting it. So that simply means the car's change in velocity in that time interval. So 30 at 30 seconds, the velocity is negative 14. Then velocity at 0 seconds is negative 20. So the difference between them is 60%. Any questions so far, A and B? Sometimes we see problems like this on free response questions where they like to play with IVT and intermediate value theorem and mean value theorem and see if students can distinguish between those two theorems. So part C, it says, can there be a time when velocity is equal to negative 5? So this one is a little bit easier because we have the velocity graph in front of us. So even though velocity of negative 5 doesn't show up, we do know that velocity is a continuous function. And just looking at these numbers here, can we guarantee that velocity is going to hit 5 somewhere in this time interval? Yes, right, because we see 0, we see 10. It can't skip over 5, right? It's got to pass through 5 in order to get from 0 to 10. So that's an application of intermediate value theorem, right? We have our target is 5. We see a value below 5. We see a value above 5, and the function is continuous. We can guarantee that there is at least one moment when the velocity is going to hit exactly 5, somewhere between 50 and 60. So. Oh, sorry, negative 5. My bad. I was thinking positive 5. So negative 5, we cannot, guarantee it because we have negative 10 at 35 seconds. We have 0 at 50 seconds. So it's got to hit negative 5 somewhere on that time interval. So since v of 35 equals negative 10, and negative 10 is lower than my target, and my target is lower than my other endpoint, which I'm looking at the 50. And I would guarantee at time where velocity must be equal to negative 5 in that time interval. Now, part D says between 0 and 60 seconds, must there be a time when acceleration is equal to 0? So this one, if we tried to do IVT, we would kind of get stuck, right? Because all these acceleration is positive. So we can't really look at this and say, okay, I can guarantee this acceleration 0. Because if I just look at acceleration table, all these are positive values. The guarantee is going to dip below dip below these positive values. So IVT doesn't quite work, but there's something else that we can use, right? Maybe we can't use acceleration, but we can rely on what to potentially arrive at this conclusion. Velocity, right? We know that velocity we know acceleration is the slope of velocity. So if I can somehow show that velocity is experiencing a slope 0, then I can guarantee that acceleration equals 0 without acceleration showing me a 0. So this is really mean valley theorem or Rolle's theorem here. So if I can find two velocity values that are exactly the same, then if I have two velocity values that are the same, then that means it's got to hit that value and it's got to come back up to reach that point. Right? Or other way around, it could have two same velocity values. It may rise and fall, but if it rises and falls, it's still going to experience a slope 0. So it doesn't matter if it's a relative min or relative max. If it hits that point and comes back to that point, that means it's got to go up and come down or go down and come up. So we do see two velocity values that are -20. So it's, in this case, you can see that -30 there. So it's probably going down and coming back up. And because of that, acceleration is going to experience 0. Because we can guarantee a slope 0 somewhere on that time interval. So we can say mean value theorem or Rolle's theorem. Either is fine. I'm going to say Rolle's theorem because it's more specific. Rolle's theorem, since velocity is continuous with brackets and differentiable on the open interval, and v of 0 and v of 25 is showing me the same velocity, there must be a value on that time interval where v prime is equal to 0. Or in other words, where acceleration is equal to 0. Okay, page 2. I think it's good to see, the way that they design many of these FRQs. Even though the stem is Riemann sums or particle motion, they're still trying to work in other concepts that we've learned, right? Like first theorem, application of first theorem, application of IVT, application of mean value theorem. So they like to kind of insert as much of the concepts that we've learned into, in a very compact form. So, but the good news is on the AP exam, you don't get everything right in order to earn points, right? I mean, in order to earn a 5 on AP exam, if you can get 60% of the problem right, if you get average, 5 or 6 points out of 9 points for every FRQ, you're still on track to getting a 4 or 5. So, typically part D is the most difficult one, but that's just the general pattern. That may not always be the case, but typically they like to kind of get you into the problem. So part A and part B is kind of warming you up, and then it gets a little bit more involved as you go further down into the FRQ. Okay, temperature of the water in the tub at time t is modeled by strictly increasing. So we know that this WT is never going to dip. It looks like it's rising, but it's giving us assurance that it's continually rising from 0 to 20. At time t equals 0, the temperature of the water is 55 degrees Fahrenheit. The water is heated for 30 minutes. So we don't see what's happening between 20 and 30. We only see the data up to 20. Values of WT at selected time t for the first 20 minutes are given. So use the table to estimate W prime of 12. So we want to find the rate at which the temperature is changing at the 12th minute. So this is just approximation here, so we just rely on slope, right? So W prime of 12, we can use what order pairs to find the slope, yeah. Yeah, so this one, because 12 lands between 9 and 15, you're forced to rely on order pairs. If you use any other order pair, you won't get full credit because this one, there's two order pairs that are obviously going to provide the best approximation. And the rate of change would be Fahrenheit per minute. Part B. Use data to evaluate the depth interval from 0 to 20 of W prime of t dt. So let's use first theorem. We know W prime will rise up to W of t, plug in 20 and 0. So just W of 20 minus W of 0. Let's find that value. We can use our table to do that. So this is basically saying subtracting the temperature at the 20th minute with the temperature at the 0th minute. So W of 20 is 75, W of 0 is 55. So that gives us 16. So what does that mean? That means that temperature is going to increase 16 degrees over the time interval from 0 to 20 minutes. Part C is average value theorem. I think within average value, they want us to use left Riemann sums. I'm sorry. That's right. No. That'll show up on the quiz too. So we go through left Riemann sums approximation, and this will give us our average temperature. And it's asking, is this an under estimation or overestimation? Well, they tell us at the beginning that this WT is strictly increasing, right? So the strictly increasing, and I'm using left Riemann sums, I should be able to convince myself, okay, this is all these rectangles are going to be inscribed. And so I should be getting an under approximation. Okay, try part D. Part D, we're going to take advantage of that formula that we've been working on. Final equals initial plus displacement, right? So if I want to find the temperature of the 25th minutes, I can pick up where I left off. The final data from the table is the temperature at 20th minute. And from the 20th to 25th minute, we can use that's W or this W prime of T to accumulate the change in temperature in that time interval from 20 to 25. So we left off at 71 degrees, and then between 20 and 25, we see the temperature is going to rise another 2.043. So we add those together. Temperature of the 25th minute will rise up to 73 degrees. Okay, I want us to be able to pace us through this packet, make sure we can get it done before next Tuesday's quiz. So your homework is page 1 through 6, and this will be due on Thursday. Okay, so tonight, just wanted you guys to focus on studying for your test. But we did the first few problems, and then you'll work up to page 6. So you'll show me page 1 through 6. And again, your homework due on time is going to add into your FRQ quiz. All right, come get your phones. Yeah. I think I'm good.